So in this video, I want to show you a graphical illustration of where using Newton's method actually fails. As you can see here, this is the cubic function, and you know that cubic has a 0 at 0, okay? So the cube root of 0 is 0, so that's pretty easy, right? But if we tried to apply Newton's method to this and we didn't pick a value close enough, say we picked an x naught here, okay? So what's going to happen if we put the starting point here? Well, we're going to bring it down to our output, and what do? We take the slope of the tangent line that goes through that point, and where it crosses the x-axis, that's our new x naught value. And so our x1 is going to be this point right here. Well, to get the next x2 value, I need to plug that into the function and find the slope of the tangent line at that point. And I pull my tangent line out here. Well, guess what? Now my new x2 is a little bit further away than my x1 was here, than my x naught was here. Look, remember guys, I'm trying to converge in on this 0 here because the 0 is right there, but it looks like we're just getting further and further away with each iteration. And so now I'm going to plug this value into my curve here, and I make a new tangent line here, and boom, this thing like goes way the heck over here and pops out that x3 there. Now if you continued this through, you can just imagine, right? Like this curve is going to slightly go up, and then that next tangent line is just going to be like way like 100 over that way. Okay, so it just keeps going further and further away from what we're trying to approximate, that real root at 0, right? So just to give you a numerical, I mean, I'm not saying that these are the exact what you would get if you ran through the Newton's method. I'm just, you know, kind of eyeballing it here. So like you start at -2, and then you jump to like 2.5 maybe, and then after that you jump to 5 over here. I guess that would be a -5, okay? And then 19 way the heck over here, right? So this thing, you know, even though the real 0 is at 0, it looks like you're oscillating between negative, positive, and your numbers are not only oscillating positive to negative, but they're also getting larger and larger and larger each iteration. Okay, so that's kind of an issue for us. So more iterations we do, the further we get from the true root of x equal to 0. While it doesn't always work, it does work most cases and generally pretty quickly. Sometimes you get in this scenario where it just oscillates and it will never converge, okay? And then sometimes you kind of get into this box scenario where it's like it shoots you to one derivative and then that derivative shoots you right back. So it's like you just keep getting, like, you'll be like 1, then you'll get x1 equal to -1, then you'll get x2 equal to 1, and you'll get x3 equal to -1, and it just never converges on any value, right? Sometimes that can happen where it just gets stuck on 2 values and oscillates. So you got to be careful on the value, your starting point, because, you know, say you so you'll see this again in numerical methods. If you take this class, this technique will pop up again. But one thing I do want to illustrate is, you know, just because it failed with that starting point doesn't mean that it would fail with all starting points. So just to illustrate that, say instead of starting at the point we started at, that we start maybe right here, okay? Oh. So let me delete this real quick. And so if I do that, it runs me up to here, And then what happens? Well, the slope of the tangent line gets me to right here. And then I plug in, and then it shoots me in even closer here, and then closer and closer. And so I am actually converging. So there's a point at which if you pick a x naught close enough, and maybe it's at these dots that I've located right here, your tangent line actually will converge in on the true zero. So it's all about the x naught that you start at, and if you pick a good x naught, you should be able to converge. Okay? All right, guys.